Hey everyone, and welcome! Today we are going to be diving into one of the absolute cornerstones of math, the world of real numbers. This is going to be a fun one, so let's jump right in. Okay, so here's our roadmap for today. First, we'll get a handle on what the real number universe even is. Then we're going to play detective and crack something called the prime number code. We'll use that code to find HCF and LCM, uncover a really powerful formula that connects them, and then, for the grand finale, we'll solve a classic mathematical mystery. So, first things first, before we get into all the cool tricks, what exactly are we talking about when we say real numbers? Let's build our foundation. Put simply, a real number is pretty much everything. It's this giant collection that includes all the rational numbers, like fractions, and all the irrational ones. The absolute easiest way to think about it is this. If you could imagine it on a number line, yeah, it's a real number. And this one category, it really does cover the whole shebang. You've got your rational numbers, like 3 over 2. You've got your irrational numbers, the ones that go on forever, like the square root of 2 or pi. Of course, all the positives, all the negatives, and 0. They all have a spot on that number line. All right, let's build on that. We're going to check out something with a kind of intimidating name, the fundamental theorem of arithmetic. But don't worry about the name. Just think of it as finding the secret DNA of every single number. So why is this so fundamental? Well, it basically says that every whole number that isn't already a prime number is built from a totally unique set of prime building blocks. It's like every number has its own special, unfakeable prime fingerprint. No two are the same. Let's actually see this in action with a number like 420. We just start chipping away at it. We divide by the smallest prime we can, which is 2. Let's do that again. Now we can't use 2 anymore, so we move to the next prime, 3, then 5, and we keep going till we hit 1. And what's left is that unique prime DNA of 420, 2 2s, a 3, a 5, and a 7. So you might be wondering, okay, cool, we found a number's prime DNA, but why? Well, because once you have it, you get this mathematical superpower. You can easily find the highest common factor, the HCF, and the least common multiple, the LCM, for any numbers. And this explains the difference perfectly. The HCF is all about finding the shared ingredients. It's only the prime factors they both have in common. But the LCM? That's about building the biggest possible combination using all the prime factors from both, taking the highest amount of each one. Okay, let's put this to the test. We'll bring back our buddy 420, and this time we'll pair it up with the number 66. So here they are, their unique prime codes, laid out right next to each other. All right, let's break this down. For the HCF, we're just looking for what's common to both lists. They both have 1, 2, and they both have 1, 3. So the HCF is 2 times 3, which is 6. Easy enough. Now for the LCM, we take the most of every single prime factor involved. That means we need 2 2s, 1 3, 1 5, 1 7, and 1 11. We multiply all of that together and we get 4620. Now, what if I told you there's a really slick shortcut? There's a formula that connects any two numbers with their HCF and LCM. It's like a secret, perfect relationship. And there it is. It's just so simple and balanced, right? On one side, you multiply the two numbers together. On the other side, you multiply their HCF and their LCM. And guess what? They are always equal. It's not just a party trick. It's a deep truth about how numbers work. So how is this actually useful? Well, it means if you have any 3 of these 4 pieces of the puzzle, the two numbers, the HCF or the LCM, you can always figure out the missing one. So let's try it out. We know our numbers are 66 and 420, and we just figured out their HCF is 6. So we just plug those numbers into the formula. Then, with a little bit of simple algebra, we solve for the LCM. And what do you know? We get 4620. It's the exact same answer as before, but way faster. Okay, so we've been working with formulas and calculations. Very certain stuff. Now we're going to switch gears and become detectives. We're going to prove that the square root of 2 is irrational using this really clever trick called proof by contradiction. The way this works is just brilliant. To prove something is true, you actually start by assuming it's false. Then you just follow the logic, step by step, until you find something that makes no sense, a total contradiction. And if your starting point leads you to an impossible conclusion, well, your starting point must have been wrong. Let's walk through this together, nice and slow. First, our big assumption. Let's just pretend the square root of 2 is rational. That means we can write it as a fraction, a divided by b. And this is key, that fraction is in its simplest form, meaning a and b share no common factors. Okay, now we do some algebra, square both sides, and we get 2b squared equals a squared. Now, here's our first big clue. This tells us a squared is an even number. And if a number's square is even, the number itself has to be even. So a is even. From there, we can use the same logic to show that b must also be even. And boom, this is the aha moment. The whole case just broke wide open. Remember our very first rule? We said that the fraction a over b was in its simplest possible form, with no common factors. But our own steps just prove that they're both even, which means they're both divisible by 2. That's a direct contradiction. They can't be both. So since the thing we assumed at the very beginning led us to a conclusion that is logically impossible, our assumption has to be wrong. The square root of 2 simply cannot be written as a nice, simple fraction. And if it's not rational, it has to be irrational. Case closed. So look how far we've come. We went from just finding numbers to finding their secret prime DNA, all the way to a seriously cool proof. The big thing to remember here is that this detective method, this proof by contradiction, is a super powerful tool you can use. You just saw how it cracks the case for the square root of 2. So, what about the square root of 3 or the square root of 5? The challenge is yours. Thanks for tuning in.